Welcome back to the deep dive. Today, we are taking a massive swing at one of the most pressing questions in technology.
The really big one.
How do we actually trust these AI systems that are being deployed so fast, especially when they're moving into fields like medicine?
High stakes life and death fields.
Exactly. We're not talking about hypotheticals anymore. Generative AI is hitting the clinic, and our sources show that the infrastructure supporting it is, well, it's dangerously underdeveloped.
That's really the core of it. The sources we looked at, they don't really focus on training a better model. They focus on building a reliable system around that model.
And what did they find?
They reveal these three sort of non-negotiable pillars for trustworthy AI. Standardized logging, fundamental reliability, so determinism, and then verifiable knowledge.
And if we don't commit to that kind of rigor, we're basically deploying systems that we can't audit.
We can't audit them at all.
Yeah.
I mean, without that consistent record keeping, you can't measure real-world performance.
You can't catch bias creeping in.
And detecting adverse events, it becomes almost impossible once you're talking about millions of patient interactions. It's a fundamental gap.
So the mission here is what? Rigor over speed.
Rigor over speed.
Oh, okay.
Because the urgency is real. Clinicians are relying on these outputs right now.
Okay, so let's unpack this. Let's start with that first pillar you mentioned, visibility.
Right.
Anyone in computer science knows about syslog, that, simple universal protocol for logging events. It's like the black box for a software system.
It is.
But our sources point out this just startling oversight. The clinical AI stack, which is moving so fast with these complex generative AIs and agents, it has no universal equivalent.
There's just no standard way to record how, when, by whom, and for whom these models are even used.
And that's the infrastructure deficit that leads to this idea of MedLog.
Exactly. MedLog is basically a proposed universal event-level logging protocol designed just for clinical AI.
So like a flight data recorder for every single AI interaction.
That's the perfect analogy. A MedLog record gets created anytime an AI model is invoked. It doesn't matter if it's a human, another algorithm, or an AI agent acting on its own.
And the sources are incredibly specific about what this log needs to capture. It's not just the model ran. They lay out 9 core fields.
And they go way beyond just basic system metrics.
Let's touch on a few. You start with the basics, right? The header for timestamps and the model instance.
Yep. The model instance field is crucial. It links the specific version that's running back to its documentation, its model card.
Yeah.
So you always have that lineage.
But then it gets really clinical. You need the user identity.
Right. So you're logging EHR identifiers, things like the NPI, the National Provider Identifier, for the doctor who asked the question.
Or the MRN, the medical record number for the patient.
And if it's an automated system, it needs its own AI agent identifier. After that, you've got the inputs.
So for a traditional model, that's the feature vector, the numbers. But for an LLM,
it's the exact prompt that was used. Or the clinical note it was summarizing. You need the raw input.
Okay, and here's where, for me, the concept really goes beyond simple logging. It's this field called internal artifacts.
Yes. This is designed to capture the AI's moment-to-moment reasoning.
So you're recording its chain of thought traces, uncertainty estimates, and things like SAP scores.
And we should probably clarify SAP scores for a second because they're so important.
Good idea.
SAP scores basically tell you why the model made a certain recommendation. It quantifies how much each piece of input data contributed.
So if a system says a patient is high risk,
the SAP score might say, okay, the number 1 reason was their recent high blood pressure reading, and the number 2 reason was their age. Capturing this lets you explain the decision later.
So you're logging the AI's internal thought process. That's what enables real accountability. And finally, you have the outcomes.
Which is the crucial link. It connects the AI's recommendation to what actually happened next.
Did the doctor accept the suggested therapy? Was the dose changed?
Exactly. And then, down the line, it links to patient outcomes. This is what gives you that retrospective view. It's the foundation for continuous surveillance.
So what does having a MedLog infrastructure actually let us do, beyond just checking a regulatory box?
It's a catalyst. It enables continuous surveillance, auditing, real-time improvement. I mean, the FDA has already said we can't expect clinicians to oversee every single output from these generative systems.
Well, it's just not feasible.
Right. So MedLog provides that operational feasibility.
Yeah.
But even more than that, it creates this new kind of digital epidemiology. We can start to connect human behavior, and even biology with how AI is influencing them.
And there's a perfect real-world example of this in the sources, a case study from Colette Health Services about an AI tool they use for predicting hospitalization risk.
Yeah, this is a critical system. It was used to trigger proactive nursing follow-ups for chronic patients, and it was working well.
But then what happened?
Well, in mid-2023, their monitoring system, a sort of precursor to a full MedLog, it detected a major gradual dataset shift.
And a dataset shift means the new data coming in started looking different from the data it was trained on.
Precisely. And the shift was in one key input, the patient's lactate dehydrogenase value, or LDH.
So what was the cause? A new disease pattern, something complex?
No, and this is what makes the finding so powerful. The cause was incredibly mundane. The hospital had switched to a new vendor's LDH testing kit back in March.
Wait, hold on. A change in a physical piece of lab equipment threw off a highly complex digital system.
Exactly. The new kit, over the next 18 months, just slightly, gradually, but consistently, changed the distribution of LDH values the AI was seeing.
And what was the impact of that?
When they simulated it, the results were sobering. Nearly 10% of patients would have had their absolute risk scores shifted by more than 0.1% just because of that new testing kit.
That sounds small, but in aggregate.
In aggregate, it degrades clinical accuracy and safety. And continuous logging was the only thing that caught this physical world change leaking into and corrupting the digital system.
That's a phenomenal illustration of why we need something like MedLog. It helps you see the problem.
Right.
But that leads us right into the next pillar. What if the problem isn't the data, but it's built into the AI's engine itself? We need to talk about fundamental reliability.
We do. And this brings us to frankly, a surprising and worrying reality.
Which is?
If you run the exact same large language model query twice, even if you set the temperature to 0, which is called greedy sampling, you often don't get the same result.
And for anyone who hasn't heard that term, temperature 0 or greedy sampling is supposed to guarantee deterministic output. It means the model must always pick the single most statistically likely next word.
It's the bedrock of how we expect algorithms to work. If you see A, you must output B. Every time.
But it fails. Why? The common explanation is this concurrency plus floating point idea, right?
Right. The hypothesis is that when calculations run in parallel on a GPU, the order of operations can change slightly. And because of how computers handle floating point numbers, A plus B plus C might not be exactly equal to A plus B plus C.
That makes sense. But the sources say that's not the main culprit here.
It's not. While that math is the underlying villain, the actual forward pass kernels, the core computational bits, are usually run-to-run deterministic if the input is identical.
So what's the true culprit then?
It's a lack of batch invariance.
Batch invariance.
The result for your single request changes based on the size of the batch it runs in. In other words, how many other people are querying the server at the exact same moment.
Wait, I have to pause on that because that is astonishing. My answer depends on whether I hit the server alone at 3 in the morning or during rush hour with 10 other people.
That's pretty much it. Since the server load is non-deterministic from your perspective, the final output you get can change.
How is that even possible? Why would server traffic affect a single matrix calculation?
It comes down to speed. To run these computations super fast on a GPU, they have to parallelize the work. And when the batch sizes are small, the kernels use different strategies, sometimes called split-K parallelism.
So instead of calculating one massive sum, they break it into little chunks, add those up, and then combine the totals.
You've got it. And by splitting the calculation, they change the order of addition. Because of that floating point issue, that tiny change in order can cause the final number to be infinitesimally different.
And that tiny difference then cascades through all the layers of the model.
Until it's big enough to make the model pick a different word. And then your whole output diverges.
And the sources say attention kernels, like in flash attention, have the same problem.
Similar headaches, yes. Getting batch invariance there means making sure the math is stable not just to the batch size, but also to how the sequence itself is processed. You have to implement fixed strategies, not just let it optimize on the fly.
And there's an incredible experiment in the sources that proves this.
Yes, using the Quinn model. The researchers ran the same simple prompt, "Tell me about Richard Feynman," 1,000 times, always with temperature 0, hoping for one single answer.
And the aha moment.
The aha moment was that they got 80 unique completions from those 1,000 identical runs.
80.
80. The outputs were identical for the first 102 tokens, but then they split. For example, 992 completions said Queens, New York, but 8 of them said New York City.
That's a small difference for Feynman, but imagine that non-deterministic shift in a clinical setting. A diagnosis, a dosage.
Exactly. And when they re-engineered the system with deterministic batch invariant kernels, when they forced it to calculate in a predictable order no matter what, all 1,000 results were identical.
Which proves it's a solvable engineering problem.
It's solvable, but it requires deep intervention in the guts of the AI engine. And the implications for training are massive. If you're using reinforcement learning, where the model learns by interacting with itself, that whole process relies on predictable behavior.
If it's not predictable,
Then your on-policy RL becomes riskier off-policy RL. The training just gets unstable and inefficient. So fixing this is a prerequisite for building reliable, self-improving agents.
okay, so MedLog helps us track behavior, and batch invariance fixes the model's reproducibility. Now, the final pillar, knowledge. How do we make sure the AI's core facts are verifiable, especially in medicine, where hallucination is a constant threat?
This is where the big generalist LLMs really struggle. If you ask an off-the-shelf model to create a rigorous domain-specific knowledge graph, or KG, from, say, a bunch of PubMed papers on diabetes, it fails.
It just hallucinates.
It hallucinates, it's sensitive to how you word the prompt, and it just has shallow domain expertise. The data backs this up. A powerful 32 billion parameter LLM only produced KGs with a fact score of 40.2%.
Wow, so nearly 60% of it is unreliable. You can't build a clinical app on that.
You can't. And this raises the question, how do you build that reliable symbolic layer of knowledge without these LLM errors? And the solution presented is a thing called GraphMERT, which is a great example of neurosymbolic AI.
Tell us about GraphMERT. It's much smaller, right? Only 80 million parameters?
Tiny by today's standards. And it's designed specifically to distill KGs from high-quality, expert-verified text, not just random internet data.
And how does it work? What makes it neurosymbolic?
It's architecture. It combines a normal transformer encoder with something called a hierarchical graph attention network, or HGAT. So think of it as a dual learning process. The transformer reads the text, and the HGAT is simultaneously learning the relationships between things in the text.
So it's aligning the words with the structure of the knowledge.
Exactly. It learns the relational knowledge abstractly. And the performance jump is drastic.
What were the numbers?
Applied to those diabetes medical KGs, GraphMERT hit a fact score of 69.8% compared to the LLM's 40.2%.
That's almost a 30-point jump. That's the difference between something dangerous and something you could actually start to use in a hospital.
Right. And its validity score, so how well it adheres to logical consistency, was 68.8% versus the LLM's 43%. It's not just more factual, it's more logically coherent for that medical domain.
And this focus on knowledge graphs, it all ties back to trust, doesn't it? What's the real value of a KG over just using a raw LLM output?
Accountability and transparency. KGs give you that symbolic layer you need for reliable applications because the reasoning is explicit and auditable. You can often verify a conclusion by just checking the path in the graph.
And crucially,
Unlike the black box of neural embeddings, KGs are editable and auditable by human experts. If the knowledge is wrong, a doctor can go in, see the error, and manually correct the graph. That enables real accountability.
so we've really gone deep into the architecture of trust here. This has been a dive into the critical but maybe not so glamorous infrastructure needed for AI.
It is. And to summarize, if you want reliable AI, you need these three things working together. You need the MedLog surveillance system, the black box, to see every interaction and catch things like that LDH testing kit change.
Right.
Then you need the batch invariant kernels to make sure the algorithms themselves are reproducible and deterministic no matter what the server load is.
And finally, the knowledge.
And third, you need those GraphMERT-derived knowledge graphs to ensure the core facts the AI is working with are structured, factual, and verifiable by humans.
So what does this all mean for where AI development is headed? It feels like the push for success is shifting.
It really is. It's moving away from just getting high benchmark scores in a lab, from building the fastest car to building the rigorous, auditable infrastructure needed for the messy, high-stakes real world.
We're moving from promises to plumbing.
From promises to plumbing.
Right.
And maybe here's a final thought. We started with the analogy of aviation safety. MedLog wants to be the black box for medical AI, recording every decision.
Okay.
But if the fundamental code is non-deterministic, if the result of a critical calculation changes based on concurrent server traffic, like we saw with the batch invariance problem, how confident can we really be in the audit trail that black box produces?
So you're saying the log might just be a record of a random event?
It could be. The next frontier of reliability has to tackle both system auditing and fundamental code reproducibility at the same time. Otherwise, what are we really auditing?